but maybe we should try to set up now. Christine can do it. Okay. So
Hello everyone, and thanks for joining in. My name is Shamit Shrivastava, and I'll be speaking on the topic of thermodynamics of propagation and interactions of spikes on self-assembled lipid monolayer. To help you orient to that topic, imagine a spike that essentially represents a local compression of a single molecule thin film of lipids or fat molecules as they self-assemble on the air-water interface. Now you might be wondering, why do we concern ourselves with such an obscure phenomena? And one motivation, at least, comes from the field of energy efficient computing. As many of you might be aware, advances in deep learning and AI are putting a tremendous demand on the computational power of conventional hardware. Therefore, the brain's energy efficiency is inspiring a new hardware paradigm known as neuromorphic computing. To give you an indication of this efficiency, consider this estimate by IBM, according to which a hypothetical simulation of the brain in real time on conventional hardware would require 12 gigawatts of power, which is peak power production of a country of the size of Denmark, whereas the human brain consumes merely 20 watts. And in fact, latest chips from Intel based on neuromorphic architecture claims to run 100 million neurons at 500 watt, which is an incredible advance by any means, but it is still off by 3 orders of magnitude when compared to the brain's energy efficiency. Therefore, the question arises, how are neurons so energy efficient? As soon as we ask that question, we essentially open a Pandora's box, because we soon realize that even in physiology, there is no satisfactory answer to this question yet. Let's start with a simple understanding based on textbook what a spike in neuron means. A spike, also known as an action potential, essentially represents a localized depolarization of the cellular membrane, which then results in these local circulatory currents that then lead to its conduction or propagation along the axon. The process is typically modeled using an equivalent circuit, where the components of the circuit actually correspond to physiological component in the cell. To get an understanding, or at least the essence of the mechanism or the physics of this mechanism, it is really helpful to refer to this statement from Sir Hodgkin, where he says that the invariance of action potential arises because the energy used in propagation does not come from stimulus, but is released by the nerve fiber along its length. In this respect, nervous conduction resembles the burning of a fuse of gunpowder and is unlike current in an electrical cable. Now, this statement is important because by disregarding the energy of the stimulus, we are essentially disregarding a role for momentum transfer, which we as might know explains or provides an avenue for the propagation of sound wave, which we know is a reversible phenomena. So the question is, can we really disregard momentum transfer and reversible propagation during an action potential at all? To answer this question, it is important to combine various observations of physical manifestations of nerve impulse. By that we mean that apart from the voltage signature of an action potential, researchers over past 100 years have also measured various other manifestations, such as the displacement of the nerve membrane as the signal passes by, or changes in interstitial fluid pressure, as well as changes in local temperature of the nerve during the action potential. And so, for example, if we look at the mechanical components of the signal, we see a clear one-to-one correspondence between the electrical and mechanical component, which essentially means that nerve impulse is actually an electromechanical wave. In fact, these kind of experiments or observations have become quite sophisticated now, and recently researchers were able to map them on the surface of a single neuron. However, the most interesting observations remain to be that of a temperature pulse that is also observed during action potential. So for example, here you can see that when the action potential arrives, there is a rise and a fall in the rate of heat production, rate of change of temperature, which coincides in a one-to-one manner with the action potential or the electrical signal. And this, according to many, is a clear indication that there is a significant reversible component in the propagation of action potential. In fact, these observations have been so important that over past 100 years, it has been repeated quite a few times by many different researchers, and some of these results are compiled here. What you essentially need to focus on is this number, which is the amount of heat produced and the amount of heat absorbed during the action potential as measured. And you can see that they are quite comparable, and which basically means that nerve impulse is largely an adiabatic or reversible phenomena. Now, in contrast, the model that we discussed predicts a predominantly irreversible character, which is due to the flow of ions through the resistors. Clearly, then, such a fundamental disagreement in the foundation of the subject should be a cause of a major concern in any field, and its resolution, at least in my opinion, would be a perfect objective for Thermodynamics 2.0. Now, noticing the electromechanical propagation of the pulse as well as its predominantly reversible nature, it has been suggested that sound waves can potentially be, or action potentials can potentially be sound waves propagating within the interface. To help you imagine that scenario, imagine medium 1 as the medium that is outside the cell, and medium 2 as the medium that is inside the cell, and then interface represents the membrane along which we know the action potential propagates. Now, this was suggested in 1989 by Konrad Kaufmann. However, as you can imagine, it was criticized immediately. And basically, the criticism was around how can sound wave explain the various characteristic features of action potential, such as its solitary propagation, that is, it propagates dispersionless and maintains its shape as it travels. There's all-on excitation. The conduction velocity can actually vary by 3 orders of magnitude between different species, and even within a single species if you vary temperature, pressure, and pH, and ions, and so on. Another really remarkable property of action potential is that when two action potentials collide, they do not pass each other and annihilate, at least in many cases. And this was really remarkable because to the best of our knowledge, such a phenomena has not been observed in the case of sound waves. So we know that sound waves can interact nonlinearly, but to completely annihilate each other was not known of. Similarly, there were many other observations and aspects of action potential which needed to be reconciled if we wanted to have an acoustic-based understanding which is consistent with the reversible nature of the action potential. It was with this motivation that the lab, my PhD advisor, essentially started working with the model system of lipid monolayer. Lipid monolayer is a classical model for biological membranes where you can characterize the system based on a surface pressure and a surface area in analogy to the pressure volume characterization of 3D systems. And this can be done nicely on a classical biophysical tool known as a Langmuir trough, where you can actually control the surface area through the use of a barrier and measure the surface pressure simultaneously. This allows you to obtain what are known as the state diagrams of the interface. As you can see here in blue, you see the surface pressure and surface area dependence. What you can also do on the same setup using different sensors, you can also measure the surface dipole or the surface potential due to the dipole moments at the interface. And you can already see that there is a non-trivial relation between the electrical and mechanical components of the interface. One can in fact repeat this exercise at various different bulk, pH, and temperatures. So for example, here a family of state diagrams have been obtained by varying the bulk temperature, and thus you have these isotherms at different temperatures. What you can also do is calculate the derivative of this isotherm at a point, and then point by point you can actually obtain the compressibility of the monolayer as a function of lateral pressure at different temperatures. Now, once we have the compressibility, the question arises, what happens to a perturbation? Does it propagate reversibly as required by the elastic nature of the interface? And this was already probed before I joined the lab. What the lab had previously shown is that if you, for example, use a droplet of a solvent like ethanol and drop it into the monolayer, surface pressure waves arise where the velocity of propagation of these waves directly relates to the compressibility as it should be for a sound wave. And in this sense, there is a clear analogy between the surface waves and sound waves. Now, what I was interested in though was the nonlinear aspect of the phenomena. So imagine now, due to these sharp peaks in compressibility, we expect a lot of nonlinearity in these waves. And if I set myself up here and then excite a pulse, it would be interesting to observe what happens. However, we realized in order to do that, we need to come up with a non-contact high-speed measurement technique, which was developed basically using a technique known as photoresonance energy transfer. So here you see we still have this good old pressure sensor of the Langmuir trough, which allows you to measure the initial state, the mean state of the monolayer. I have this piezo cantilever that perturbs the interface along the surface by forming a meniscus. Then at a certain distance at C, I actually measure my optical signal, which allows me to see the distance between the molecules and their relative orientation with respect to each other. So now imagine if a compression wave comes by, I would be able to pick up changes in distance as well orientation between the dipoles of these molecules, which was the point. So I start by obtaining a compressibility profile as we saw earlier. We identify 3 different regions where we'll try to create the spike and then make the observation, and we see that the most remarkable signal indeed appears near the phase transition. So system actually starts to spike when we are close to the phase transition, and whereas if you are away from the phase transition, you see these weak dispersive waves that travel. So this was already very interesting. What made it much more interesting was the striking resemblance of the spike with the shape of an action potential, the first action potential that was measured in a squid axon in 1945. Without going too much into the detail, let me emphasize that the shape was actually quite important because it contributed majorly to the current understanding of electrical components based understanding of action potentials. So next, basically then wanted to see the threshold phenomena we talked about. So now what happens if I sit close to this nonlinearity and excite with different strengths and see what happens. I did that. We are basically hitting the blade harder and harder, and at some point the spike suddenly appears. This can be resolved much nicely as here, and you can see that the response of my system is nonlinear with a clear threshold and a saturation of amplitude as well. So this also now shows, so our compression waves in the lipid monolayer show a very remarkable property of all or none of the action potentials as well. Next, the third remarkable property, which was basically the collision aspect. So now we have a pulse traveling in the negative x direction and a second pulse traveling in the positive x direction, and we vary the amplitude of the incoming or negative x direction pulse and see what happens when these two interact, which is plotted here. So here you can see that in black we have the measured outcome of the interaction, whereas in red, a dashed line, we have the expected signal based on simple linear superposition. And as you can see, as we increase the strength of the excitation of one of these pulses, it was only at maximum amplitude of both of the pulses that we see a clear indication of annihilation. And we could measure this, and it was up to 80% annihilation that we observed. So this was really fascinating because prior to this, we had no knowledge of such a phenomena existing in the acoustic framework, basically annihilation of 2 acoustic pulses upon collision. So this was all great, but what is the mechanism? How is this all happening, and why it's happening near phase transition? A really important insight came from the observation of evolution of these pulses over distance. As you can see here, I have measured these pulses over distance, and what you see is that at some point these become unstable and the pulses actually split. What you can also see is the front part of the pulse actually travels with a constant amplitude and a constant shape for quite a significant distance, while the following wave decays quite rapidly. This actually led me to the very important literature on splitting of shock waves, and especially shock waves near phase transitions, which turned out to be the key to understand everything. So briefly, what you are seeing here is basically a superheated shock wave followed by a condensation part of the pulse that takes the system through the phase transition. And while this is happening, there is an internal heat transfer where the latent heat of the phase transition is actually passed on to the front running wave, maintaining its shape and amplitude. This phenomena is well known and is referred to as a polytropic phase transition, polytropic detonation, and that basically explain our observations. And in fact, if you are interested to go deeper into the shock physics behind all of this, why it becomes interesting near phase transition, how are these equations solved, and how does it apply to a lipid monolayer, please have a look at this latest preprint where I summarize all these results and also get into the physics of all of it. So finally, to conclude, we go back to this statement from Sir Hodgkin, and we now realize that it doesn't have to be either or case between momentum transfer and energy release. For example, gunpowder can be burnt but also detonated, and such combination is basically allowed in the framework of shock and detonation physics. However, this framework is fundamentally different from the current purely electrical understanding, and a compromise is actually not possible. To highlight this, consider this quote from von Neumann, where he explains what the essence of detonation is. Basically, we are disregarding the possibility that detonation is propagated by special kind of particles, this is important, moving ahead of the wavefront. Indeed, if the views which we propose are found to be correct, no such particles will be needed to explain the detonation wave. And now, finally, looking forward, it is based on this understanding of detonation that we have proposed a new element for the lipid monolayer, where it essentially reimagines how a synapse or a node of Ranvier might work, and this we believe would be really important in eventual application of these lipid monolayers as a truly neuromorphic platform for neuromorphic computing. Thank you, and I'm happy to take any questions.
Thank you very much. Questions, please? Yes, so I would have a question which relates to models of spikes, neuronal spikes in other systems. I think there is some history of this in chemical waves. So, for example, Belousov-Jabotinsky reactions and things like that, and there the waves annihilate.
Yeah.
And also, spikes have this death phase. So once a spike is initiated, there is a time for which you cannot initiate another spike. And I also think the BZ has that property. So basically, yes, my question is are your mechanically generated waves, do they have this death phase, and how do you connect them to the chemical models, neuronal?
Yeah, that's a really good, really great question. Can everyone hear me? Can I come? Yeah, okay. So yeah, that's a really good question. We actually do see refractory period in our waves. And I mean, right now, right now, the way we explain it is because being close to the phase transition is so critical. And the refractory phase that you also saw in the pulse shape, right? So there is basically, and that is appearing purely out of inertia, right? So in our case, that's just a consequence of the inertia that the pulse has to relax and goes the other way. And so basically in our case, it is basically in the phase space, there's a distance from the excitability state, if you may, and that induces a refractory period. To answer your question regarding chemical waves, so basically, I mean, if you go into the detonation literature, right? So chemical waves are in a sense subsonic, or you can call them flame propagation, right? So that's essentially the question. And I mean, the question would be, in other words, it could be said that we are not ruling out that chemical waves do not exist. But, and of course, I mean, everyone is studying chemical waves, so that's not a problem. The problem is that detonation kind of waves in biology are missing. And if you basically look at the whole solution set, if you just have a general mass and heat transfer problem, they form two solution sets, right? Supersonic and subsonic. And so biology is subsonic all the way, but here we showed that it basically you can have supersonic and sonic speed propagation in membranes. And I think that is really the missing physics that needs to be combined. Also, I mean, I haven't talked about this in this presentation, but basically, we should not forget that these were lipid dipoles. And so essentially we have shown in our papers that there is actually a reversible coupling, for example, of pH. So as the pulse travels, there is a local change in pH that travels along with the pulse due to the electrostatic changes at the interface. So yeah, it's all there, and it's really, really interesting.
Thank you so much. Thank you. Very interesting. So
I had a question, if I can, and follow up on.
I'm sorry to say, just to stay in time, let's start with the next presentation. And if you can stay just a little bit in 20 minutes, then we can probably go into the discussion. Okay. So